This is the last lesson on the exponential function. We are going to talk about the final parameter, b. So just to recap of what we've done so far, we have learned about two parameters for the exponential function. One of them is a and one of them is c. A is the initial value of function, and for word problems, it's where the problem begins. It's the start. It is where the function crosses the y-axis. And c was known as the multiplicative factor, which told us if the function was increasing or decreasing depending on whether c was greater than 1 or between 0 and 1. And for word problems, c tells us how the function changes, how it grows, how it decays, and we had that fancy rule where we have to put the percent over 100 and we would get our c. I would like you to compare these two graphs. So here's a graph, it's got a pretty simple curve here versus this graph here where it's kind of deeper. So this is a pretty simple curve. This is a deep curve. This rule here is a simple y is equal to 3 times 2 to the x. This one, however, we add a 4 in front of the x. So our x is being multiplied by 4. That's why all of a sudden it goes, and then shoots up because our x is getting 4 times the size. So it's going 4 times faster than if our x was just simply 1. So let me introduce you to our new friend b, and our rule becomes y is equal to ac to the power of bx. Technically, our b's in the past was just 1, because you're used to y is equal to ac to the x. B was just an imaginary 1. But now, b is going to start changing. If b is small, like for example, 0.5, the graph will become flatter. As you can see, the graph is pretty flat here because we have a small fraction in front of our x. So it's half of x. As b increases, becomes greater than 1, say, the curve of the graph deepens. So if we go back to our original graph that I showed you in the last slide, our x goes up 4 times. Not half as much, but 4 times faster than it would if it had nothing in front of it. Let me superimpose regular graphs to you. Here we have b is 0.5, so b is half of x. We're multiplying x by a half, so it's pretty flat. Here is our simple b is equal to 1, so it's just ac to the x, and it's a pretty normal curve. And then down here in our red, we have b is equal to 4, so x is being multiplied by 4, so 4 times faster. So now you understand what b does specifically on the Cartesian plane. But what's the point, really? Understanding a and c was already enough. We were first introduced to it on the graph, then I showed you its purpose in word problems. And that is what b is there for. B is a different way to answer word problems. Do you remember in our last PowerPoint, I gave you this question that we went over in every single slide, just until we actually knew how to solve it. I said to you, bacteria grows by 12% every hour. If at the start there's 100 bacteria, how much bacteria will there be after 4 hours? Well, we did the work. We found our A, which was 100. We found our C, and we know that our X is in hours. How much bacteria will there be after 4 hours? We just put our exponent to the 4, and we got 157.35. What if I tweaked this question? What if I told you that bacteria grows by 12% every 15 minutes? If at the start there's 100 bacteria, how much bacteria will there be after 2 hours? In this case, in this question, bacteria grows by 12% every 15 minutes, so it's increasing. So our C is going to be 1 plus the percent over 100, which is 0.12. So C is just 1.12, the same thing as the last PowerPoint. This is where it gets more complicated. We start at minute 0, we have 100 bacteria. But now we have to go every 15 minutes. So For the first 15 minutes, we multiplied 100 by 1.12, our C, our multiplicative factor, and we get 112. Then again, we add 15 more minutes, we multiply that by 1.12, and we get 125.44. Again, we add 15 minutes, we get to 45 minutes, and we multiply our last value by 1.12, and we get 140.49. And we do this continuously every 15 minutes. So 15, 30, 45, 60, then an hour 15, then an hour and 30, then an hour and 45. And we keep multiplying our numbers by the multiplicative factor until finally, after 8 steps, we reached 2 hours, and we find out that after 2 hours, the number of bacteria will be 247.60 bacteria. There actually needs to be a faster way, because imagine if I had given you something like 4 hours. You would have had to do this table and have all the 15s going by 15 up until you reach 4 hours. There's a faster way. The question that you need to answer in this case is, how many 15 minutes are there in 1 hour? 15, 30, 45, and then we hit 60. There are 4 15-minute periods in an hour. It's a quarter of an hour because it's 1/4. There are 4 15-minute periods in an hour. We know that our answer is 247.60 based on the graph, so keep that in mind. We know that our A is 100 because that's how much it starts at. We know that our C is 1.12, we already talked about that. And we also know that our X is 2 hours. Now, if we plug that into our original rule that I taught you the last time, you would have 100 times 1.12 to the power of 2 hours, X, and it gives us Y is equal to 125.44. But that's not our answer. We know what our answer is. We are missing the every 15-minute part. Now that we know that there are 4 15-minute periods in an hour, how about we multiply the number of hours by 4? Because per every hour, there are 4 15-minute periods. So bacteria will grow 4 times every hour, since it's every 15 minutes. And if we do that, we get our new exponent, which is 8. And when we solve, we get the answer that we had when we did our really long table. Okay? And again, we know that there are 8 steps because we know that there are 4 15-minute periods per hour. Let's test it out with other numbers now. What if I told you that bacteria grows every 15 minutes for an hour and a half? What changes? Our X changes because it's an hour and a half, so 1.5 hours. But it's 4 times every 1.5 hours. So all we get here is we multiply it in and we get our exponent is 6. And at 1.5 hours, there will be 197.38 bacteria. And sure enough, if we look at our chart, at an hour 30, it is in fact 197.38. What if I tell you that bacteria grows every 15 minutes for 45 minutes? 45 minutes is 75% of an hour, or 0.75 of an hour. So knowing that 15 minutes happens 4 times in an hour, we keep our 4, and in this case we change our X. Our X is 0.75. And if we do the work, our Y will be 140.49, and if we double check back on the graph that we made, at 45 minutes, in fact, there are 140.49 bacteria. So after all of this, what is B? B is, in a fancy way, the number of periods per time unit. So in our example, the time unit was hours and the number of periods was 4, because for every hour, there are 4 15-minute periods. So please remember that our new equation looks like Y is equal to A, which is our initial value, times C, our multiplicative value, or our change of time, to the power of B, which is the periods, times X. And X is usually, and always will be, time. The rule for our example, therefore, would be Y is equal to 100 times 1.12 to the power of 4x. 4 being b, 4 being the number of periods per hour. Now that you know this, try and solve this question. The number of cells in an environment doubles every 15 minutes. Initially, the environment contains 1,000 cells. Consider the function which associates x to the number of hours since the beginning and y to the total number of cells. What is the rule of this function? And I expect it to be in the y is equal to ac to the bx form. What is the number of cells after 3 hours? So ask yourself if 3 is x or y in this case. And after how many hours will there be 1,024,000 cells? Answer this question on your own. The answers are on the last slide. Here are some more questions to help you test yourself on finding B. Initial number of bacteria is 200. The number of bacteria doubles every 20 minutes. Your x is in hours. Find B. Initial value of a computer is $1,300. The value decreases 1.4% each year. Your x is in years. Find B, and if you want, find the function rule. Initial number of elephants is 150, and the number of elephants decreases 50% every 5 years. X is in years. Find B. And the initial amount of investment is $4,000. Your interest is 6.4% annually, and your x is again in years. Find B. So this concludes the end of exponential functions. We have started off basic with the y is equal to c to the x. We went a bit further and added a, and now finally we've finished with y is equal to ac to the bx. Our next function that we will be learning are step and piecewise functions.